Good morning, everybody. So we're going to carry on where we left off at this slide, which is an example of a residue curve that involves azeotropes. So the type of problem that I'll give you in the assessments is, I will say there's a mixture of A, well, let me get the pointer, a mixture of A and B and C, and I'll give the boiling points of those compounds, of those components, and I will say C and B form an azeotrope at 400 Kelvin, and I'll say A and B form an azeotrope at 389 Kelvin. And then I'll ask to show the arrows on the residue and draw in a few representative residue curves on the diagram. I'll be giving you a blank ternary diagram, so it will have those triangles in light pencil transcribed across it, and you'll be able to, I will also say at what percentage those azeotropes occur. So this one looks like it is at about 50%, and this one is at 60% C. So note it is closer to C, so it is 60% C, 40% B. That's important, that you should be able to place positions on such a ternary diagram. Right, so what do you do first? The first thing you'll do is to do the the arrows on the axes. So if you start with the easy one, this one, A and C, do not form an azeotrope. A boils at 398, C boils at 409. So A is the most volatile. If it's got the lowest boiling point, it is the most volatile. And therefore the residue curve, remember, that the residue is what's left as you're boiling off this mixture. So if you're boiling off a mixture of A and C, the mixture will slowly get more and more rich in C. And eventually you'll land up with only pure C in the residue as that last molecule evaporates. Then you can go over to the azeotropes themselves. So D has got a lower boiling point. And A. So a residue curve will go from D towards A. You can fill in that. You can fill in. Is somebody else controlling my pointer? Huh. All right. So so you can fill in. You can fill in the. You can fill in that arrow. Yeah. My pointer just slow or what? Over here from D to B, D has got a lower boiling point than B, which makes D the most volatile, and the arrow will go from D to B. E is also a low boiling azeotrope. It's got a lower boiling point than C or B, and therefore the arrows move away from E. Oh, so I've just got bad internet. I'm just going to test my internet speed. I'm going to use my cell phone to test the internet speed to see what could be the problem. No, my internet speed is good. Strange. Let me just check that I'm at the right router. Yeah. All right. Well, we'll just, hopefully it'll go away. Okay. So Now you've got the arrows that are on the axes, and now you must recognize that there must be a distillation boundary where there's an azeotropic dip. In other words, a boiling point low that runs from D to E. And so you can fill in a curve. You wouldn't know what the shape of that curve is, but it will run from D to E, and this curve looks as good as any to join D and E. So it wouldn't really matter which one you choose in the test. You could have done a straight line, but it doesn't really matter. But you must recognize that this is a distillation boundary, and what that means is that if you've got a feed that occurs somewhere in this boundary, DEB, it's impossible to get a product from that distillation column that lies outside this triangular shape of DEB. So you can get, for instance, something that has this composition, D and E azeotrope. Well, it's a mixture of D and E azeotrope, but it contains both A, B, and C. And on the other side, at the bottom of the column, you will get B, pure B. And that would be with a feed that lies somewhere along that line, that straight line. So let's have a look. Again, in the tests and exams, what I will do is to say I will give you a feed position, and let's give the feed position as X, which oops, there it is. It's at the right position. So there's the X. Where's my pointer? There's the X. So it lies in this distillation region, and it is a mixture that contains not much A, not much B, but a lot of C. And I ask you to shade in the areas of possible distillate and bottoms composition. So yesterday I was showing you how you can take a line from the stable node and take it through that point until you reach a distillation axis is the same as a distillation boundary. And there's the line that we're taking. Similarly, you can take a line from the unstable node. Let me just point. I have got line selected, and I can take it through that same point to the first distillation boundary. In this case, it's an axis. Right, so remember that it's only, let me get back to my pointer. It's only this part of the line that is on the other side of the residue curve compared to the unstable node that is of relevance. So it is this part of the line that's of relevance. And for this one, it is this part of the line away from the stable node that's of relevance as one of the boundaries of the possible distillate compositions. And the other boundary is the actual distillation curve, the actual residue curve. So let's take this the unstable node, and we've got this as a boundary, and we've got the residue curve that goes through that feed point as the other boundary. So that will run along this way, and that makes up the possible bottoms compositions. So I'm going to get another color and a pencil. Choose the pencil first, and I'll choose red, and I'm going to color in the possible. Can you see while I'm drawing?
So not while you keep it in. As soon as you
Okay.
release, it's fine.
You can see fine.
Yeah.
Okay, and then on the other side, it's much more difficult in this case. And what we want to do, we think the area lies. Whoops, let me get my pointer again. We suspect the area lies between this residue curve and the distillation boundary. So it's a very small area there where we can get possible distillate compositions. And that is in fact the only area. It's possible that the area between that boundary and there could be a possible area that can be shaded. And the only way to test it is to actually try and put a point over there that goes through the feed, see if you can cross the residue curve on the other side. And in fact, you can. So this area here, that very thin area between the blue line and the black line, that is a possible area of residue of distillate composition. This area here between the black line and the blue line, and the black line and the other black line, the distillation boundary, that is also an area of possible. So let me get my red pen again, the pencil, and try and draw something that lies over here so that you can see. That is a possible area. Oops, and that one has just gone out of the blue, but that is a possible area over there. But the main area that's important is this one that lies on the distillation boundary. Over there. So that means, let me get my pointer again. This is a possible bottoms composition. And if you've got that bottoms composition, you can draw a line through the feed point and touch any one of these compositions along here. So let me draw a line as an example with a different color. We go to orange. And now I can draw a line from that composition through the feed point. Yes, that's right. I can draw a line through the feed point, and let's go straight on to the axis. And that represents, let me get my pointer again. This is a specific distillation column that has got only B and C at the bottoms, and it's got a mixture of A, B, and C at the top of the distillation column. So obviously that's not very useful, and the one that you would probably want to use will be, let me go back to line, will be one that goes from D through the feed point, and that's exactly the same as the blue line that we've made previously. So we're going from D through the feed point and landing up on that line. And remember, the rule is that such a line goes through the feed point. This represents the separation into this stream at the top of the distillation. Oops, back to pointer. This stream at the top of the distillation column, this feed, and this stream at the bottom of the distillation column. I've forgotten what I needed to say there. After getting the pointer, I'd already forgotten what I wanted to say. Okay. Yes, so this is the most useful thing. We will have a binary mixture of A and B, and a binary mixture of B and C if we do this distillation. The alternative is that we go from C and we make that. So then we'll have at least one of the components of that distillation will be pure. And then we will have a mixture A, B, C. And that mixture can change because let's notice this residue curve has got a certain pressure at which it is valid, 1.03 bar, 1.013 bar. And if we change the pressure, let's say to 4 bar, it is possible that we're going to get a residue curve boundary that instead of lying where it is now, it lies there. It can change as you change the pressure. Will you ever ask us to determine, oh wait, just missed that one. Going to chat. The feed composition on the curve. No, I can't. Oh yes, Dr. Evil would love that. Because you know that we're starting at one point, and to determine the feed, I would have to know one point and the other point, the compositions of the top and the bottom, and then you can draw the straight line, but then you don't know where on the feed it lies. So the only way you'll know where on this line it lies is with the actual flow rates. And then if D has got a flow rate proportional to this length, and this bottom's composition, or this bottom's composition, has got a flow rate proportional to this length. Oh, gee, pointer. It's got if the bottoms has got a flow rate that is proportional to this length, then you would know where the feed line went. So if you know the proportion of flow rate of D to the bottoms, you would know where the feed would be. So yeah, I've never asked it. It doesn't mean I can't, but yeah. Okay, so let's carry on. So if you change the pressure, it is possible that this distillation boundary could move from here to further away. So that if you do this distillation where you make pure C and you land up at that distillation boundary at 1.031 bar, 0.13 bar, it is possible to distill within this new boundary. So it is possible, let me get a green line again. It is possible with that feed, I'm going to just draw a feed over there. It is possible to make pure B that goes through that feed. Oh gee, wait. Now I really messed it up because I can't get rid of that alone. So choose the line shape. Yes.
So I think it's possible to select and press the delete. If you select an object you created and press delete.
Yes.
Last time we added. Yes.
Okay, let me try the pointer first. Oh yes, that looks good. Haha, yes. The teacher. Thank you, Yakuluri. Right. Now I'm going to draw that line again. Better. So once you've got a distillation column that makes this composition where the green cross is, we can distill that at 5 bar. Like that. And now we can make something that's back in the original, that's back, oops, pointer. You can make something that's back at in the original distillation boundary. So now you've got, so now you started off with ABC, that feed. You've made pure C, and you've made this ternary mixture over here. And now you've made pure B, and this mixture over here. And now, how are you going to make A? I would suggest, it's going to be difficult on this case. Okay, but at least now you've got A, B, and C. If you recycle, you will start pushing, you will start feed, recycle this stuff here. I'm just waiting for my cursor to find me. Recycle this stuff here, and you mix it with the original feed. Come on. Mix it with the original feed. You get Right, let's move on to the next slide. All right, so again, this is a better representation than all my little lines that I've been drawing. So you've got a azeotropic system. That's a normal, ideal vapor law equilibrium. So this is the most volatile component, L. This is in between, and H is the heaviest component. H for heavy, L for light, right? I for in between. Okay, so if we start with F, you can make pure H, pure heavy, and you can make a mixture of L and I. Or with that feed, you can make a pure light component, and you can make a mixture H and I. And this is going to be the bottoms. Oh, why did I say B for pure L distillate? Pure L. Yeah, pure L is the distillate. That's right. And this is the bottoms for the pure, if you have pure L distillate. This is the distillate if you're going to have pure H as the bottoms. And again, you only look at the line from that bottoms after it's crossed the feed. That's one of the boundary lines. And the other boundary line is the line that goes, the residue curve that goes through the feed. Okay, again on this one, take the H, straight line through the feed, and it's the line on the opposite side of the feed that forms the boundary. And how do you know that? What you have to do is to choose possibilities. If you choose this possibility over here, you can go through the feed, and it is possible to cross that same distillation curve at some point on the other side of the feed. But if we choose another one, now I'm going to go back into drawing lines. If we choose another place, like over here, I'm just going to make a cross. Oops. If we make a cross over there, I wanted to use a line tool. If that is the bottoms composition, we go through the feed, and we can never cross that same residue curve. So we were starting on this residue curve over here, but if we go through the feed on the other side of the feed, we can never cross that residue curve. And then it's obvious that the best you can do is when you start here or to the left of this pointer, so that you can get to H, because H is where all of the residue curves intersect, and they don't go any further than that. So that's the beauty of these residue curves. It gives you so much information graphically. All right, let's go on to this one we've already discussed. And here is a ternary azeotrope. In other words, this point marked T is the lowest boiling point on the, whoa, it is the highest boiling point. 2, 3, it's an interesting one. It's not, it's a saddle point. There's the lowest boiling point. And that point is the unstable node. All of the arrows are moving away from that point. And then over here, we've got an intersection of the distillation boundaries. And from that point, you've got, it is a saddle point because you've got one residue curve coming in, or two residue curves coming in. There's one from each side. And from there, they move away this way, and they move away that way. Both L and G unstable nodes. Yeah, you're right. Both of them are unstable nodes in this case. Let's have a look at the other azeotrope. This one is a high boiling azeotrope because all of the arrows are going towards it. That's a stable node. B is a saddle point. A is a saddle point. So we've got two stable nodes because C is another stable node. Right. So C and E are stable nodes. L and G are unstable nodes. Thanks, Jared. Right, so in this case, if you've got a feed in this position, you can only distill within the distillation boundary. So I'm going to point out the distillation boundaries if my cursor follows me this time. That way, that way, that way, and up again. That's a distillation boundary, and therefore, when you do your areas of possible distillate and bottoms, this will be possible area of bottoms because all the arrows are going towards that point, and this is going to be the possible distillate composition. The same applies to any of these four areas. If your feed lies in any one of these four areas, you cannot distill outside of that area. So if your feed lies over here, you can only distill to make A, L, T, E, that area. Interesting one, this one. Okay, so that doesn't help you. What it means is that at a certain pressure, it is impossible to move out of one of those distillation areas. But I've already showed you that if you change the pressure, the placement of these distillation areas actually moves. The placement of the plot, where this thing plots on the ternary diagram, actually moves. And that allows you to cross distillation boundaries because as soon as you do a distillation at a different pressure, you have a different distillation boundary. Okay, now we're going to get really complex. And I don't want to go into this. I don't want to go into this in this lecture because I'd like to spend an entire lecture on it. So the problem is, we know with distillation of ethanol and water, let's say we've got a feed that lies over here. Normally the feed is going to lie down here somewhere. With fermentation, you will get probably 10% ethanol in water, so it will lie well down this thing. But if you distill water and ethanol, there's an azeotrope that occurs here at 351.2 Kelvin. And therefore, this is a distillation boundary that if you start outside of that distillation boundary, in other words, where you're starting with F over here, it is impossible to distill outside of that distillation boundary. So it's impossible to get to B2, the pure ethanol that you would be looking for. And so the question is it possible to add something that is immiscible with water, toluene? If you add toluene to the system, is it not possible to break the distillation boundaries without changing the pressure? And that is pretty much what this diagram is about. So that is something that I'll do in the next lecture. And so you can think about that. In other words, what you're going to try and do is to arrive at this point, because if you take the product from a distillation column that lies at this point over here, 347.4 K, and you cool it down, you can get a, let me get a line again. You can get a composition change, because that will be one liquid phase, two liquid phases. If you put in that as feed, you get two liquid phases, one with that, oh wait, I have to go back to the pointer. One with that composition and one with that composition. And that way you can mean these three distillation boundaries. Okay, the distillation boundary. Yeah. Did somebody want to say something? And then here is another distillation boundary. And here's another distillation boundary. And the way you can go from one distillation, from you starting at this distillation boundary, one way you can go in between, you can cross distillation boundaries, is using the liquid-liquid equilibrium. That is for next lecture on Monday. Okay, so time for questions. Are you all stunned, or are you just finding it easy? Oh dear. Yeah. Remaining slides. Yeah, this is what's coming tomorrow. But it shows, what it shows is that you can actually design a new process. All these lines here represent the streams that you get as you make separations. And there's the decanter, which runs across over there, and then two distillation columns, one distillation column that runs along this red line down to your feed, down to below your feed, and then this is the other distillation column. And then what you do is you have D1 and S2. This is just as a preview, D1 and S2, which you mix together. So there again is the lever arm rule. If we take S2 and D1, there's D1, there's S2. We mix them together, we can make M2. And that's how we move into that distillation region. Once we've got M2, we put it into a distillation column. We can make pure ethanol up here. And we can make this mixture, which is in a different distillation, which is possible to put into a decanter. As soon as you get D2 up there, cool it down, and you can decant. All right, but that, I'm just giving you an introduction to just be prepared for the next lecture that we'll have on Monday. So, Rich, trying to understand how to reason with the line we draw, the basics of line drawing in residue curves. Yeah, that is, go back to one of the first slides we had in this section, in the residue curve part of the course, and that was the lever arm rule. And so the lever arm rule says if you've got a feed such as this one, M1, and you draw a straight line that covers the same residue curve. Now this residue curve, the one that goes up here, makes a sharp turn it makes a sharp turn at the azeotrope, and it comes down this line. That is the same residue curve. It's crossing on each side of the feed. The feed is M1. That's the distillate. And that residue curve that the distillate is crossing goes up all the way down, and therefore on the other side of the feed, it crosses the same distillate over there. It crosses the same residue curve over there. Yes, Jacques-Louis.
So in last week's TUT, we had that separation column, separation train design, and
yes,
there was this. When me and a friend looked at it again, we came up with a thing where you work towards the ternary mixture, and then use the what was it? The
Tedder and Rudd.
Yeah, Tedder and Rudd. Those heuristics about which method is most economic.
Yes.
Is that something to consider always, to try and work towards a ternary mixture and then work towards trying to find the most economic solution, or rather keep it simple with just splitting binaries?
No, I think the best way to go is to try and use as many heuristics as possible. Whether you get to a ternary mixture or not. So for each, the first column, choose the column and the separation that's going to give you the most possibilities of heuristics that are applicable. And then you would go to the next column, and depending on those choices you made in the first column, you might get many heuristics or fewer heuristics that are applicable to whatever separation you choose next. And that would be the most important, rather than trying to get to a ternary mixture. But if you happen to get a ternary mixture, then that would be the way to go, to use Tedder and Rudd once you get to a ternary mixture.
Okay, not cool.
And remember that is only to do with ordinary distillation. So the part we're doing at the moment is when you have azeotropes, then those same heuristics don't apply anymore.
Yeah. No, so that's for zeotropic ternary distillation.
Yes.
Okay.
So Jared, so apply heuristics, and if you hit a ternary, then you evaluate. Yes, apply heuristics, and only if it happens to be a ternary, then you can start doing Tedder and Rudd. We'll do some examples, whether it's a class test or a TUT. We will do some examples where you use Tedder and Rudd. All right, I'm going to switch off the recording.